In this video, we're going to go over section 3.1 and 3.3 from our textbook. So we're going to start with the complex number system. And we'll start with defining I here. So I is an imaginary number, and it's going to be equal to the square root of -1. And then I squared is going to be equal to -1. And we can see this because if we were to do the square root of -1 times the square root of -1, the square roots would cancel, and so we'd be left with what's on the inside, -1. Now, numbers of this form here, where a and b are both real numbers, are called complex numbers in standard form. So a would be called the real part of our complex number, and b is called the imaginary part. And so here are some examples here. Now, the complex number system is an extended number system that includes the real number system as a subset. So what this means is that real numbers are also complex numbers, but in the case where we just have a real number, we say that we have 0 imaginary part, just like this here. We have -8, that is a real number, but just with 0 imaginary part. All right. Now, if we just have 3i, that is also a complex number. It is imaginary, and we just say we have 0 real part in this case, and so on. Okay. Now, I want to look at this expression here. So if we have an expression of this form for a greater than 0, then the square root of -a is going to be equal to I times the square root of a. So let's look at some examples of this. We have the square root of -12, so that's in this form here. So this answer is just going to be I times the square root of 12. But the reason why we get that is because this is the same as the square root of -1 times 12. Then we know that we can break these up into two radicals, like this here. And we just saw from above that the square root of -1 is equal to I. So we would write this as I times square root of 12, and that's where this comes from. Similarly, for this example here, we can do the same thing. This negative is going to stay out front, but we have -1 times 81 in our radical. So we'll get negative. All right, and then this negative is going to stay out front, and we know that the square root of -1 is I. We also know that the square root of 81 is 9. And so we would write this as -9i. So that's just the form that we would write it in. Our imaginary part here is always our number and then times I. All right. Now we can also multiply and divide expressions involving expressions of this form. So for example, if we want to multiply the square root of -2 times the square root of -25, we can do the same thing. So we would get I times square root of 2 on that side, and this is multiplying I times the square root of 25, which is 5. So in this case, we end up with, since we're multiplying all of these guys, we end up with I squared, and then 5 times the square root of 2. So we would write it like this. Now remember, I squared is equal to -1. So we can just rewrite this as -1 times 5 square root 2. So this just becomes -5 square root 2. All right, let's look at this example here. We're going to divide these guys. We have the square root of -32 divided by the square root of 8. So we'll do the same thing here in the numerator. We have -1 times 32 under our square root. And then we just have the square root 8 in the denominator here. So in the numerator, this becomes I times the square root of 32. And we know that when we divide two square roots like this is the same as taking the square root of their quotient. And so in this case, we have 32 divided by 8, which is just 4, so we get I times square root of 4 here. Now we can add or subtract, multiply, and divide complex numbers as well, not just expressions of this form here. So let's look at these examples here. We have 2 minus 3i minus negative 5 plus 2i. So we know that this is just the same thing as with 2 minus 3i, and then this negative here is going to distribute to both terms in the parentheses here. So we end up with positive 5 minus 2i. So in this case, we can just combine like terms. We have just a 2 and a positive 5 here. And then we also have a minus 3i and a minus 2i. We have negative 3 i's, and then we're going to take away 2 more of them. So we're going to end up with 2 plus 5 is 7, and we have minus 3i minus 2i, so we're going to get minus 5i. Similarly, for this example here, we're going to multiply these complex numbers, and we can do that just how we normally did it with real numbers. So we'll do the FOIL method. So this term is going to multiply that term and this one. And then this term is going to multiply this one and this one. Okay, so we end up with 1 times 7 is 7, and then we have 1 times minus 4i, so it's going to be minus 4i. Then we have 2i times 7, so that'll be 14i. And then we have 2i times negative 4i, so we get minus 8i squared, since we have an I times an I here. Alright, and now we can do the same thing by combining our like terms. We just have this 7 here, but we have this minus 4i and plus 4i, so that'll be positive 10i. And then we have this minus 8i squared. But remember, I squared is equal to negative 1. So this is minus 8 times negative 1. So we'll get 7 plus 8. I'll write that step out. We have a positive 8 here since we have a minus 8 times negative 1. And so we end up with 15 because we have 7 plus 8 plus 10i. All right. Now, when dividing complex numbers, we want to eliminate the imaginary part of the denominator. So for example, this here, so that our result is in standard form, so the standard form of our complex numbers, which was the a plus bi. And we can do this by multiplying by what's called the complex conjugate. So the complex conjugate of the complex number a plus bi is going to be a minus bi. And their sum, and their product is going to be the sum of the squares of their real and imaginary parts. So what we'll do is, for example, we're going to multiply the top and bottom of this fraction by the complex conjugate of our denominator. And so we do that because remember we don't want an imaginary term in our denominator, and we know that when we multiply by the complex conjugate, it does get rid of that imaginary term. So, for example, here, we're going to multiply the top and bottom by the complex conjugate of our denominator, so that's going to be 2 minus 6i. And remember, when we have something divided by itself, this is just equal to 1, so we're just multiplying this by a factor of 1. So, and just to be clear, this is the complex conjugate of our denominator here. So we're going to multiply straight across our numerators and our denominators. And then foiling the top and the bottom, we'll get 16 minus 48i minus 6i plus 18i squared. And in the bottom, we're going to get 4 minus 12i plus 12i minus 36i squared. So just by foiling, like how we did in this last example here. So simplifying and combining like terms, we'll get 16 minus 54i, and then we have plus 18 times negative 1, since I squared is equal to negative 1. Then we have 4, and then we have minus 12i plus 12i, so this goes to 0 here. So we'll get 4 minus 36, and again, multiply that by negative 1. Right? So in the numerator, we're going to get 16 minus 18. So we'll get negative 2 minus 54i. And in the denominator, we get 4 plus 36. So we'll get 40. So this is equal to negative 2 over 40 minus 54i over 40. And then we can simplify each of these guys. So we'll divide by 2. So we'll get negative 1 over 40 minus 27i over 40. Oh, sorry. We're dividing it all by 2, so our denominator should be divided by 2 as well. All right, so that is our answer there. And so as you can see, we accomplished our goal by getting rid of the imaginary part in our denominator, and we did so by using the complex conjugate. Okay, so now this is written in standard form for our complex numbers, where a is negative 1 over 20, and b is negative 27 over 20. All right. So now we're going to move into section 3.3. We're talking about solving quadratic equations. So remember from the last section, this function here is our quadratic equation written in standard form. Now we've seen this from multiple different videos, but the zeros of this quadratic equation are going to be the same thing as the x-intercepts and the solution set of this quadratic equation. And each is solved by finding the numbers that will make this statement here true. So the first method we're going to look at to solve a quadratic equation to make this here true is the zero product property. So if a and b are complex numbers and a times b is equal to 0, then either a is equal to 0 or b is equal to 0 or both. So let's illustrate this with an example here. So we have this quadratic equation, and we want to figure out for what x values will make this equal to 0. So we know that in order to do that, we can factor this guy. We've seen that in previous sections. So factoring this, we need two numbers that will multiply to be 4 and add to be negative 3. So we'll get x minus 1 times x minus 3 here. And so what we're saying is that in order for this to be equal to 0, either this product or this product needs to be equal to 0, or both. Because if, let's call this one a here, and this one b here. Right? So if a times b is equal to 0, then a needs to be equal to 0, or b equals 0, or both. So that's what that's saying here. So this tells us that in order for this to be 0, we need x minus 1 to equal 0, or x minus 3 equals 0, or we can have both. So what we'll do is we'll solve for x for both of these guys. So for this one, we'll add 1 to both sides, and we get x is equal to 1. And for this one, we'll add 3 to both sides, and so we get x is equal to 3. Okay. So this tells us that 1 and 3 is the solution set of our quadratic equation, as well as the x-intercepts and the zeros. Okay. So our solution set is this here. All right. The next thing we're going to look at is the square root property. So the solution of this here is either going to be one of these three cases. So if k is greater than 0, then our solution set is going to be plus or minus k. If it's equal to 0, then our solution set is going to be equal to 0. And then if our k is negative, the solution set is going to be this imaginary number here, or plus or minus this imaginary number here. So what I mean is, let's look at these examples here. If we're given this quadratic equation here, we want to solve for x. We want to figure out for what x values we'll make this equal to 50, and we can do that by solving for x. So the first thing we'll do is divide by 2 on both sides. So we get x squared is equal to 25. And we need to get rid of this square root, so we'll square root both sides of this guy. And so what we end up with is x is equal to negative 5, or x is equal to positive 5. Right? And this is the case since both negative 5 squared is equal to 25 and 5 squared is equal to 25. Okay? So when we have this, that's when we would write x is equal to plus or minus 5. So just indicating that we have two solutions, the minus of this or the positive of this. So this tells us our solution set for this guy is negative 5 and positive 5. Similarly, let's look at example B here. So we're going to do the same thing. We need to solve for x. So we'll square root both sides here. This tells us that x is going to be equal to the square root of negative 64. And we saw from the last examples, this is the same thing as this here. And so we get the square root of negative 1, which we know is I. So I'll write this here. And then the square root of 64 is going to be plus or minus 8, which is equal to plus or minus 8i. And we know that this is true since we have minus 8i squared. What we're going to get is positive 64i squared. And we know that I squared is equal to negative 1, so this makes this minus 64. And similarly, 8i squared, we're going to get positive 64 times I squared, which is negative 64. So our solution set is minus 8i and positive 8i. And lastly, let's look at this example here. This is a little bit different, but we still have the form of something squared is equal to something else. So we'll just solve for x here, so we'll divide by 3 on both sides. So we'll get x plus 2 squared is equal to 9. Taking the square root of both sides here, we get x plus 2 is equal to plus or minus 3, since the square root of 9 is 3. So in this case, this tells us that either x plus 2 is equal to negative 3, or x plus 2 is equal to positive 3. And in this case, we'll have x is equal to negative 5 by subtracting 2 on both sides. And in this case, we'll have x is equal to 1 by subtracting 2 on both sides. And so in this case, our solution set is negative 5 and 1. We can also use the quadratic formula to solve quadratic functions. This is especially helpful when we maybe can't factor a quadratic function, for example. And so the quadratic formula is given by this here. And I believe in the PowerPoint slides on Pearson, they do show you how they got this formula. But for now, this is all we really need to know. And so let's look at this example here. We're going to solve this guy using the quadratic formula. So the first thing we're going to do is write this in our standard form of a quadratic equation. So that is x squared minus 5x plus 7 is equal to 0. So we just added 7 to both sides of our equation. And the next thing we're going to want to do is identify our a, b, and c's. So a is going to be 1, b is negative 5, and c is equal to 7. Okay, so that'll make it a little bit easier when we're plugging it into this equation here, or this formula here. So let's go ahead and do that. We'll have x is going to be equal to minus b. We know that b is already minus 5, so this means b is going to be positive 5. Then we're going to have the square root of b squared, so that's going to be, we'll just put that in. Then minus 4 times a, which is 1, and then times c, which is 7. And then this is going to be all over 2a. So we'll get 5 plus or minus square root. We'll have negative 5 squared, which is 25, minus 4 times 7, which is 28. And this is still all over 2. I'm sorry, this is over 2 times a, which is just 1. So this will be over 2. Then we'll get 5 plus or minus the square root of negative 3. So we have 25 minus 28, all over 2. And we know that when we have an expression of this form, it's just going to be I times square root of positive 3. And this will be all over 2. Okay. So this tells us that our solution set is going to be 5 over 2 minus I square root 3 over 2, and 5 over 2 plus I times square root 3 over 2. Alright, so the last example we're going to look at is one where we want to solve a quadratic inequality. So this example here. So the first thing we're going to do is, again, just write this in standard form. So we're going to add 32 to both sides here. So we'll get 4x squared minus 24x plus 32. And we want to figure out for what x's will make this greater than 0. Now we will be able to easily factor this, but the first thing that I'm going to do is take out a 4 from each of these terms, because they're all, 4 is divisible, 4 divides each of these terms. So we'll divide by 4 on both sides, just to make this a little easier for us. So we get x squared minus 6x plus 8 is greater than 0. So we want to figure out what numbers will make this greater than 0. Well, like I said, we can easily factor this guy. We need two numbers that will multiply to be positive 8 and add to be minus 6. So this will be minus 2 and minus 4. So now we want to figure out when this will be greater than 0. And remember, we are multiplying these two guys here. So we're going to separate these into, we want to figure out when x minus 2 is going to be greater than 0 and x minus 4 is going to be greater than 0. Since we are multiplying these, we need both of them to be positive, right, in order to get a number that's positive. Or we need both of these numbers to be negative. Right? Since a negative times a negative will give us a positive number, and in that case, we will have that this will be greater than 0. So, for x minus 2 to be greater than 0, we need x to be greater than 2. Right? Anything smaller than 2 here, if we were to plug that in, we'd get a negative number, so this wouldn't be greater than 0. Similarly, for x minus 4 to be greater than 0, we need x to be greater than 4. And on this side, for x minus 2 to be less than 0, we need x to be less than 2, and x to be less than 4. Okay. Now notice here, let's draw a little number line for us. So we have 2 and 4 here. Notice on this side here, if we were to have both of these numbers to be positive, we need x to be greater than 2 and x to be greater than 4 for both of these to be positive here. So when I say x is greater than 2, that's everything in this region, but I also need x to be greater than 4 as well. So that takes away everything in this region, and so we need to look at everything in this region. Okay? So essentially, if we are looking at x values that's greater than 4, it does also imply that we're looking at x values greater than 2. So we're going to take these x values here. Similarly, on this side, if we're looking at x values less than 4, that's going to be everything in this region here. And if we're looking at x values less than 2, that's going to be everything in this region over here. And remember, we need both of these numbers to be negative in order to multiply to get a positive number. So we need both of these conditions to hold. So we need x to be less than 4 and less than 2. So that eliminates everything in this region. So we're just going to look at everything in this region. So we need x to be less than -2. So this tells us, and we'll write this in interval notation. Like we said, we're going to look at everything in this region here. So from -infinity up to 2, and we're looking at everything in this region here. So from 4 up to infinity. And so this would be our solution set, all of the x values in these intervals here. All right, and the last thing we'll go over is just understanding the solutions to quadratic equations graphically. So if you're given a graph like this here, we know that the solutions are going to be our x-intercepts. And so looking at a graph, we should be able to see exactly where the zeros are just based off of where it intersects our x-axis. So in this case, the solution set, if our quadratic equation is equal to 0, will just be these two numbers. If it's less than 0, it's going to be the interval from a to b. And if it's greater than 0, then it's going to be the union of these intervals here. And so we actually saw that in this example here. Similarly, if we have our quadratic equation, if it has a minus a, we get this here. Also, if we have that our quadratic equation only had one solution, so it only intersected the x-axis at one point, we would get this here. And then we would get this case if our quadratic equation indicated that our parabola opened downwards. Okay. And lastly, if we have something like this here, we see that our graph is not intersecting the x-axis at any point for either of these. So this tells us that we have no zeros in both of these cases. So our solution set when p of x is equal to 0 is going to be the empty set, and when it's less than 0, in this case, it's going to be the empty set as well, because all of our output values are positive. It's above the x-axis. And so this tells us that when our quadratic equation is going to be greater than 0, that's going to occur everywhere. So all real numbers here. And similarly for this guy, we know that when p of x is equal to 0, it's going to be 0 because there's nothing intersecting our x-axis here. So we get the empty set. And again, we know that when p of x is less than 0, this is going to be all real numbers because our outputs are all below our x-axis. So these are all negative output values. And on the other hand, we know that that whenever our quadratic equation is going to be greater than 0, we're going to get the empty set, since it will never be above our x-axis here. All right, so that'll be it for this video.